Okay, so we left off last time talking about factoring using, we started talking about factoring using some patterns, right? Using the sum and difference of cubes patterns. Remember from earlier, last unit, when we were solving quadratic equations by factoring, we learned that there is no sum of squares pattern, and we all know the difference of squares pattern, right, that we've used already. But the difference of cubes and the sum of cubes are a little bit, those are new, right? And they're a little bit bigger. Just a quick reminder of how we can memorize these things, how we can, we can associate, how can we, is there a little pattern we can see here? Yeah, there is. If we're doing a difference of cubes or a sum of cubes, we know that they're going to break into a linear factor that has the terms a and b, right? And a quadratic, an irreducible quadratic factor that's got an a squared, an ab, and a b squared. It's just what are the connecting operations? What are the sign? Are there pluses or minuses in between? Here's the pattern. If it's a difference of cubes, so a cubed minus b cubed, well then the sign in the linear factor is minus. So that's always going to, and that's always going to be that way, right? If that's an a cubed minus b cubed, then it's an a minus b. Then it flip-flops, it alternates. So the first operation in your quadratic factor is a plus in this case. And then the last one is it's always a plus b squared, right? The last one's always positive. But it goes same, opposite, plus every time. Same, opposite, plus when you're doing sum or difference of cubes, okay? All right. We looked at the example if we wanted to solve x cubed minus 8, right? And if we solve this by factoring, we got the real 0, 2, and we got the complex conjugate pair, -1 plus or minus the square root of 3 times I, right? And we didn't get those. Remember, if we just tried to isolate the x, we only got the real one, right? And so the moral of the story there was, if you want to find, if I've got something bigger than a quadratic expression that I'm finding zeros for, right? I'm trying to solve any kind of equation bigger than quadratic. I can't just isolate the x anymore. I have to use factoring patterns to find all of the complex zeros, the ones that are non-real, the ones that have i's in them. Yes, ma'am. Exactly. If the degree, and let's go back and let's review a couple of those theorems that we talked about too before we jump any further. So the fundamental theorem of algebra tells us that every polynomial function of degree n, where n is some positive degree, has exactly that many zeros, n zeros. So an nth degree polynomial has n complex zeros every time, right? As long as we're including multiplicities, right? So factors that show up more than once, so they show up to a power, then those count as multiple factors, right? Okay? So for example, like down here, we looked at an example where we had something like this, right? This appears to only have 2 factors, even though if I were to multiply this out, it would be a cubic polynomial. But because the x minus 2 factor is being squared, it has a multiplicity of 2. It shows up twice, counts as 2 factors. Okay? Make sense? Okay. We had a couple other little things that we added. Remember we added, where is it? There it is. The complex conjugate theorem tells us that imaginary roots or zeros always occur in complex conjugate pairs, right? They always come in pairs. And so remember we said, like, if we had a 5th degree polynomial, there's only 3 possible outcomes for the types of zeros we could get. We could get 1 real 0 and 4 complex zeros, 2 pairs of 2. We could get 3 real zeros and 1 pair of complex zeros, or they could all be real. But you could never have 2 real zeros and 3 complex zeros, because the complex ones always have to come in packets of 2. They always come in pairs. Okay. All right, I think we're up to speed. Let's try something like that. Just get a little practice. So how are we going to solve this equation? Say it again. We could try that. Does 54 go into 2,000? I don't think it does. I don't think it does. So we probably don't want to do that because remember, we can't isolate x. Now, if I'm just trying to find the real zeros, yeah, I could just isolate the x. It's fine. I could do that. But I want to find all the zeros. Okay, so if I want to find all the zeros, what am I going to do here? Right, I've got to use a factoring pattern. Okay, set it equal to 0. Good. So we're going to add the 2,000 to the other side. So we put it into standard form, right, where it's set equal to 0. 54 x cubed plus 2,000 equals 0. And remember, the whole point here is we want to be able to factor this thing into a product of factors so we can apply the zero product property. Okay, now we run into a little bit of a snag, right? Because what's the only pattern that this could fit? I've got something x cubed plus a number. What's the only pattern that could potentially fit? So yeah, in this case, it'd be the sum of cubes, right? Everybody see that? So the only pattern it could fit. So we want to be able to write this thing as something cubed plus something cubed. 54 is not a convenient cube, is it? It's not a perfect cube, nor is 2,000. Is there something we could do here, though, to write this in a way where it would look like maybe something cubed plus something cubed? What do you think? Say it again. Okay, what would that be? We want to be able to write this as something cubed plus something cubed. 54 is not a perfect cube, but what is there a perfect cube factor of 54? Something that divides evenly into 54 that is a perfect cube? Nine's a perfect square. So think about if we made a list of perfect cubes. So perfect cubes, what would they be? Well, 1 cubed is 1. 2 cubed is, 3 cubed is, 4 cubed is. They grow pretty fast, don't they? 5 cubed. Good. 6 cubed. There you go. 7 cubed. 343. Is that right? Yeah. 8 cubed. I think it's 4. Oh, did I? Let's see. 7 cubed. 7 cubed. 8 cubed is, no. 8 cubed is not 912. 512. There you go. Good. Yeah, I think you said 912. I was going, boy, that can't be right. 9 cubed. 729. 10 cubed. Look how fast they start to grow, right? Those are, it's a bigger list, isn't it, right? Okay, well, we could keep going with that, but what are the only perfect cube factors that are less than 54? Well, it's just these guys up here, right? 8 doesn't go into 54, right? We can cross that one out. 1 we don't really care about, right? 27 does, though, doesn't it? 27 goes into 54 how many times? Twice. Okay, so what if we try factoring out of 2? Okay. If we factor out a 2, that gives us 27x cubed plus 1,000. Oh, that works, doesn't it? Okay, that works. Equals 0. So are we going to get any solutions from that too? No, it's just a variable, or just a constant, right? So we could, if we wanted to, we could factor it out, or we could just divide both sides by 2. Right? Remember, we can divide both sides of an equation by a constant, and that's okay to do. We just can't divide both sides by a variable. So we get a little simpler equation to solve. 27x cubed plus 1,000. That looks like a difference of cubes, doesn't it? That looks like, or sum of cubes, sorry. That looks like, what is being cubed in that first term? 3x, okay? So we've got the quantity 3x cubed plus 1,000 is just 10 cubed, right? So now that fits our pattern, doesn't it? That fits our sum of cubes pattern. So let's see if we can remember how to do that. A cubed plus b cubed is going to be what? Hey, let's write it out. Okay, here's how I remember this, right? We know that the linear one is always, linear factor is going to have an a and a b. The quadratic factor is going to have an a squared, an ab, and a b squared. Now we just got to plug in the operations. So what goes there? Plus, because remember it's same. What goes there? Minus, and what goes there? Plus. That one's always plus, right? So same, opposite, plus, okay? All right, so what's that give us then? So that gives us, instead of an a, we've got a 3x. Instead of a b, we've got a 10, right? Instead of an a squared, this is a tricky one. You got to think about this. Instead of an a squared, what do we get? Not that tricky, but it's a common mistake people make is on this term right here. So a is 3x. What's a squared? It's not that tricky. 9x squared, right? People sometimes want to do 3x squared there. It's just, for some reason, it seems like that's a common mistake. So we get a 9x squared minus, what goes there? Say it again. 30x, good. 3x times 10 plus 10 squared. There it is, right? We got it factored, okay? So now we can apply the zero product property, right? So we got 3x plus 10 times 9x squared minus 30x plus 100 equals 0. All right, so what's our real 0 then? If I set 3x plus 10 equal to 0, what's the solution? X equals what? You can do that one in our head if you... Negative 10 thirds, right? We're going to isolate x, we're going to subtract the 10 to the other side and divide by 3, right? So there's our real solution. But we've got to find the zeros of this quadratic factor also. And remember, this one's always going to be irreducible. There's no way to factor it. We just always have to apply the quadratic formula. And we already know we're going to get i's in our answer, right? So, oops. So we got to use the quadratic formula, right? Our solutions are going to be x equals negative b. So that's 30 plus or minus square root of b squared. What's 30 squared? 900 minus 4 times 9 times 100, all divided by 2 times 9, 18. Okay, so 30 over, we can split this up. 30 over 18 is going to reduce to, oh, what is that? So 6 goes into both of those, so 5/3 plus or minus. Now, what about this radical? So we're going to get 3,600 in here, aren't we? 900 minus 3,600 would be negative 2,700. So all that stuff is going to be the square root of negative 2,700. Okay, so what goes into 2,700 that's a perfect square? Well, 100 does, right? Everybody agree? So I could split up 2700 up into 127. That's going to give me a couple of 10s. And then here I've got a 9 and a 3, don't I? And then the 9's going to split up into a couple of 3's. And so I get 30 radical 3, right, times I, right? And then 30 over 18 was just 5/3, wasn't it? Right, so we end up with our other solutions are x equals 5/3 plus or minus 5 radical 3 over 3 I. And there's our three solutions, right? We got a complex conjugate pair, and we got a real solution. Okay? How are we doing with that? Is that good? Okay. Okay, what about something like that? So it's bigger than x squared. So what do I probably want to do with this? I can't just isolate x directly, right? What am I going to do here? Okay, so put it in standard form, right? Set it equal to 0. There's a good first step. Now what? What do you think? Does that fit any patterns? Think back to our patterns. X to the 6th minus 64. So it's x to the 6th minus a number. So what are the only two patterns we know that could apply here? Difference of squares, okay? Or the other one would be difference of cubes, right? Those are the only two that could apply. So could I write this? And there's two options here. We're going to see which one is better, okay? So how about option A? Could we write this as a difference of squares? Could I write x to the 6th minus 64 as a difference of squares? Something squared. In other words, something squared minus something squared. X to the 6th is what squared? Yeah, x cubed, right? Because remember, we have a property. We know that if I take a to the m to the n, if I take a power of a power, that's the product of the, I multiply the exponents, right? Okay. So I could write this as x cubed squared minus 64 is 8 squared, right? Okay, there's one option. Agreed? Okay. The other option is, could we write this as a difference of cubes? Well, yeah. X to the 6th is what cubed? X squared, okay. 64 is what cubed? 4. Okay, so let's see what happens here then. So if we do difference of squares pattern, we know we've got a squared minus b squared, right? So this whole thing is just going to split up into a minus b, right, times a plus b. Agreed? By the difference of squares. Okay. Well, then look what I get when I look at those two factors. Those are a difference of cubes and a difference of squares, right? I've got x cubed minus 2 cubed times x cubed plus 2 cubed, right? We could just think of this as being a 2 cubed, and a 2 cubed. And so then this one's going to split up using our difference of cubes pattern. I get a cubed minus b cubed is a minus b times a squared plus ab. Gosh, this happens about once a period now. So frustrating. Went years with this never happening once, but something's different. Oh, I didn't do any of that stuff? Are you kidding me? Oh, my goodness. All right, so what do we have here? We had okay, we were doing difference of squares. So we broke this up into a minus b times a plus b. And then we're going to split each of these using difference of cubes, right? So we recognize that 8 is just 2 cubed. And we got a minus b times a squared plus ab plus b squared, right? From this guy. Now we got to do this one. I get a plus b times a squared minus ab plus b squared. And all of that is equal to 0. Okay? All right, so maybe we don't even have to finish this, but do you guys recognize that we could get answers pretty easily there, couldn't we? Right? We're going to, look at our zeros that we have. X equals 2. X equals negative 2. And from here, we're going to get 2. I can just apply the quadratic formula and get 2. We should probably do it. I'll go through it fast. So if I apply the quadratic formula here, what's going to happen? I'm going to get x equals negative b, so negative 2, plus or minus the square root of b squared minus 4ac, so minus 16 over 2. So what's that going to give me then? X equals negative 1 plus or minus the square root of negative 12 is going to be 2 radical 3, and the 2's will cancel. So I'm just going to get that. Okay. How about this one? Same, almost the same math, right? If I set this equal to 0 and solve, I'm going to get x equals negative b, so that's going to be a positive 2, plus or minus, same stuff inside. B squared minus 4ac is going to give me 4 minus 16. So I'm still going to get my negative 12 in there, divided by 2. And so I end up with almost the same. I get 1 plus or minus square root of 3i when all the dust settles. Okay? There's all 6 of my solutions. Okay? Not a bad deal. Okay, what would have happened here? We can shut this one down pretty fast, I bet. The other alternative we had, option 2 here, was to think of this as a difference of cubes first. Tell me stop when you see why this is a bad idea. Okay? So we took this thing and we wrote it as x squared cubed minus 4 cubed equals 0. Okay, so that's a difference of cubes, right? So that's going to look like a, which is x squared, minus b, which is 4. Okay, well, there's our plus and minus 2, right? That's no big deal. But look at this other ugly thing we get. I'm going to get a squared, that's x to the 4th, plus ab, 4x squared, plus 16 equals 0. That's kind of ugly, isn't it? Right? It's going to work, but if I want to solve this equation right here, I've got to think of this as being x squared squared plus 4x squared plus 16, and I've got to solve the quadratic equation for x squared, right? Because this is a quadratic expression in packets of x squared only, right? And so I would get x squared equals negative b plus or minus the square root of b squared, so 16 minus 4 times 1 times 16, so minus 64 all over 2. Well, look what's going to happen here. I'm going to get x squareds equal to, I'm going to get i's in my answer. Then I'm going to have to square root these expressions that already have square roots in them and i's. That's getting ugly fast, isn't it? Everybody agree? So can we safely say here that we're just going to say no to applying the difference of cubes first? We always want to apply the difference of squares first when we're dealing with something like this. Okay? All right. Give me 1 to 5 on that. Does that make sense? Okay. It's going to take a little practice, but I mean, I think you're going to be good. Oh. Okay, what about this one? We maybe don't even have to do the whole thing here. We can just set it up, and then hopefully I have a little time where you guys can start this assignment. Yes, ma'am. Yeah, you bet. Go ahead. So what would I do here? Okay, so set it equal to 0. Good. So we've got 128x to the 7th minus 2x equals 0. Okay, good. Now what? X to the 7th is pretty ugly. That's not going to fit any pattern, is it? But what could I do? What do I always want to try to do first? Factor out a greatest common factor, so I could undistribute a 2x, and then what's left behind? Well, that's going to give me 64x to the 6th minus 1, right? Okay, now this one we could do as long as we remember, I want to break this up into a difference of squares first, right? And we won't even do the whole thing. But I could split this up then into 2x times, if I think of this as being, I guess I need to write that. If I think of this as being eight x cubed squared minus 1 squared. Everybody see then I could split this apart into a minus b times a plus b, right? Anybody see that? And now all I'd have to do is break these up using difference of cubes and sum of cubes, and we're done. Okay? I won't even do it, right? But it's the same thing we did last time, right? This would just be, I could think of this as being 2x quantity cubed minus 1 cubed, right? And just split it up using difference of cubes. Same thing here. Everybody good with that? I won't even, I mean, you want me to do it? I think you're better off just starting your assignment. We can go through another one of these later if we need to. I'm going to shut her down there. This, the assignment should be available. This is the one on binomial factoring patterns is what we call this. Let me make sure it's working.